Okay, the last theorem we're going to look at in this chapter is the divergence theorem. This theorem is due to Gauss, so it's also usually called Gauss's divergence theorem or Ostrogradzi. I think it's a Russian mathematician. So this one is just gives you a connection between the flux of vector field F through the surface S, and it connects that with the integral over the volume of the region enclosed by S. S here this time is actually a closed surface. Okay, so again, we're not going to prove this one, but we're just going to work through some examples to demonstrate how this theorem works. Okay, so in this first example, find the flux of F through the closed surface S, where the vector function or vector field is given by this, and S is the surface bounding the solid enclosed by the plane x plus y plus z equal to 1. The plane x equals to 0, plane y equals to 0, and the plane z equals to 0. So the flux is this side of the theorem. So we're going to use the theorem, and I think we're going to find that it's shorter to work out the volume integral. So again, first thing is to make a sketch of the situation. So the first thing we need to do is to make a sketch of a plane. Okay, this plane, when y and z are equal to 0, x is 1, that's going to be 1, 0, 0. When x and y are 0, z is equals to 1, that's going to be 0, 0, 1. And then when x and z are 0, y is 1, it's going to be 0, 1, 0. So plane is going to go something like this. Okay. And then of course z equals to 0 is xy plane. Y equals to 0 is the xz plane, and x equals to 0 is the zy plane. So the shape we have here is a prism. So the flux of this force field through the surfaces of this prism, we are going to evaluate by working out the volume integral of the divergence of F. Okay, so the first thing we're going to do is to work out divergence of F, which is simply going to be 2 plus 3 plus 9. So divergence of F is going to be 2 plus 3 plus 9. There is a typo. This should be 13 here. Should be 13. So just make sure I correct that typo. Okay, 2 plus 13 plus 9 is actually 24. Then we're going to have to do a volume integral over this prism. You're going to have to go and remind yourself this if necessary. So it's just going to be the integral of 24. We're going to start with the z integration, then we'll do y. then we'll do x. You can choose any iteration of your preference. So in what we're doing, first we're integrating from z equals to 0, which is the xy plane, to this plane. So that's the z equals to 0. That's going to be 2z equals to 1 minus x plus y, which is basically this plane. Then we're going to go from y equals to 0. Y equals to 0 is there, and then to that y there. So if we just put z equals to 0 here, it's going to be 1 minus x. So it's going to be 0 to 1 minus x. And then the last one is going to be x, which is simply going to be from 0 to 1. Okay. Then we do the integration. I'm not going to again stress you with the details. So this one is going to be just x minus y minus 1 minus x minus y dy dx. Then we integrate this one partially with respect to y. So it's going to be y minus xy y squared over 2 1 0 to 1 minus x. Then if we do the algebra, it's just a bit of algebra. Remember the 24, so the 24 is here now. So 24 there, 24 there, 24 there. Okay, after a bit of algebra, okay, not too much. This is going to be 1/2 minus x plus x squared over 2. Then we do the last round of integration. Going to give us 24 into x over 2 minus x squared over 2 plus x cubed over 6, 0 to 1. And our final answer is going to be 4. So that's the flux of f through that closed surface. And B, imagine, okay, so this time the function, vector function f is given by that, and the surface is the surface bounding the solid enclosed by the hemisphere. So z equals to 0 at the bottom, and z equals to the square root of that at the top. So again, just a quick sketch. So we basically just have this hemisphere here. So this is the base of it. So we're going to do the divergence of f. It's going to be 3x squared y squared plus z squared. And then if we plug into the right hand side of the divergence theorem, so this is going to be the volume integral of 3 into x squared plus y squared plus z squared dv. Since this is a sphere, it's only natural to introduce spherical polar coordinates. So if we do that, this is going to be 3 rho squared, So rho squared there. Then the Jacobian, if we're going from Cartesian to spherical polar, is rho squared sine phi. Okay, where phi is the solid angle, sine phi. Then this is d rho d phi d theta. Rho is going to range from 0 to a. Phi is a solid angle, so it's going to go from 0 to pi on 2, and then theta from 0 to 2 pi. Again, we can work these integrals separately. If we do the rho one, so we're going to have rho to the power 5 over 5, 0 to a, and then we can do the phi one. So integral of sine is going to be negative cosine. Phi is ranging from 0 to pi on 2. Then there is no theta here, means the integral of theta is just going to be 2 pi. If we plug in accordingly, this is going to give us 6 pi a to the power 5 all over 5. So it's going to be the flux of that vector function through that closed surface. Okay, in this number 2, we're going to verify the divergence theorem for the solid region bounded above by the paraboloid z equals 9 minus x squared minus y squared, and below by the disk x squared plus y squared less than or equal to 3. Where f is equal to, there is an error here. This should be less than or equal to 9, because it's basically the point where z equals to 0 is the intersection of z equals to 0 and the xy plane. So the first thing we're going to do is we're going to start with making a sketch. So it's your xy z. So the paraboloid is just going to be just a parabola. So it's going to look something like that, and this is going to be the circle x squared plus y squared equal to 9. So this here is z equals to 9 minus x squared minus y squared. So this has got two surfaces. There's this one here which we're going to call S1, and then the bottom disk which we're going to call S2. Okay, but we're going to start with the double or triple integral side of things. So the triple integral of the divergence of f dv. Now, so we are going to start with working out the divergence of f. There is our f there. So the divergence is simply going to be 2 plus 2 plus 6. This is going to be 10, which means this is going to be volume integral of 10 dv. If we employ cylindrical polar coordinates, then we can integrate this from z equals to 0 to this top surface there. So it's going to be from 0 to 9 minus r squared. Then we can integrate with respect to r is going to be from 0 to 3. Okay. Then we integrate with respect to theta is going to be from 0 to 2 pi r dz. So that was our first iteration, dr. Then d theta. So this is going to be 10 into the integral of, if we do the z integration here, it's just going to give us 9 minus r squared into r. Okay, then we are going to follow up with the integral with respect to r. So there's going to be 9r minus r cubed. So it's going to be integral of 9r. It's going to be 9r squared over 2 integral of r cubed is going to be that from 0 to 3 d theta, and then the theta integral, which is going to give us 2 pi. So if we multiply, plug these in and then multiply by 2 pi, this is going to give us 405 pi. So that's the one side of the divergence theorem. For the other side, we've already mentioned that we're going to have two surfaces here. We're going to call this one S1, which is the parabolate, and then this one we're going to call it S2, which is the circular disc. So S1 is z equal to 9 minus x squared minus y squared. What we're going to do is we're going to write this as a function of x, y, z. So bring everything to the same side. So that is going to be z plus x squared plus y squared minus 9. Then the normal vector is just going to be the gradient of g. Okay, so the gradient of g is going to be 2x, 2y, and then 1. So when it comes to the surface integral, so that's our flux through S1. So this is going to be f dot grad g ds1. So if we plug in, f is 2x, 2y, and 6z. Grad g is 2x, 2y, 1. Then we're going to look, since the parameters are x and z here, it's just in terms of x and z, sorry, x and y. If we express this in terms of x and y, then we can do the limits just in terms of x and y. Okay, so if you remember that z is 9 minus x squared minus y squared. So we can take that and plug it in here. So ds1 here. So let's do the dot product. So dot product is going to be 4x squared plus 4y squared, then plus 6z, but z is 9 minus x squared minus y squared, and so this is just going to be let's just call it ds1 still, but this the limits are just going to be now in terms of x and y, and we know that in terms of x and y the extent of the paraboloid is just from 0, 0 to the boundary x squared plus y squared equals to 9. So what we're going to do at this point is we're going to convert to polar. It's going to be 54 minus 2 into x squared plus y squared. If we simplify that, ds1. So if we convert to polar, this is simply 54 minus 2r squared, r dr d theta, r from 0 to 3, theta from 0 to 2 pi. Then this is going to be 2 pi from the theta integration. This one is going to be 0 to 3. If we evaluate this is giving us 405 pi. So that's from that's the flux through the first surface. The second surface is x squared plus y squared less than or equal to 9. So again we're going to parameterize that, and so the parametric formation is going to be r cosine theta, r sine theta, z equals to 0 this time. Okay, the normal vector is going to have to be downward vector because this is a closed surface. So we say it for closed surface, the normal must be outward. So the normal here at the bottom needs to be downward, and so that one we're going to obtain by doing r partial with respect to theta, partial with respect to r, and we're going to get 0, 0, negative r. Okay, remember that f, so f at along the surface is going to be, so it's 2x, which is 2r cosine theta, 2r sine theta. Then we've got 6z, but z is equal to 0. Okay, then if we do the dot product of f and n, this is equal to 0, which means that the flux through S2 is going to be 0. So the total flux is just going to be that through S1, which is the 405, going to be 405 pi plus 0. Okay, which is the same as the one we obtained using the double integral approach. Okay.